Hello. Hello. Today is our first lesson in right triangle trigonometry, which is our first lesson in trig. However, it's not really a full first lesson because you've already seen it a little bit in geometry. So we're just kind of revisiting some topics. So the first thing that we want to remind you of, or I want to remind you of, is that for it to be right triangle trig, guess what, guys? It has to have a right triangle. So you're definitely looking for that. We are going to be working with triangles later on that don't have right triangles, so it's kind of important that you know that. Then the next important thing is to identify where that angle is in your triangle, so that when you are working with it and you're deciding what is the opposite, which would be the side that's directly across from it, and the side that's adjacent, which is this side right here that is directly attached to the angle, you won't get those in the wrong spot. The hypotenuse never changes. The hypotenuse is always that side that's opposite the right angle, so it's going to be this side right here. So that's always stationary, but the other two can change depending on if your theta is up here or your theta is down here. And we use theta as that symbol for the angle. So in the things that you learned in geometry, that's this first group, you learned that sine of theta is the opposite over hypotenuse, and you learned that cosine of theta is the adjacent over the hypotenuse, and you learned that tangent of theta is the opposite over adjacent. So those are all things you come into this trig unit knowing already. That is only half of the trig ratios. The second half of the trig ratios are called the inverse functions, and they are cosecant of theta, which is hypotenuse over opposite, secant of theta, which is hypotenuse over adjacent, and cotan of theta, which is adjacent over opposite. So if you're looking and observant, I think you see the relationship here, right? If this is sine, then cosecant is its reciprocal. So sine was opposite over hypotenuse, so cosecant is hypotenuse over opposite. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. Tangent is opposite over adjacent. Cotan is adjacent over opposite. So whenever I'm having to solve a triangle, I'm doing these 6 ratios, I usually pretty much solve them in that pattern, so that I don't really have to recalculate this. I just know it's a reciprocal. So sine and cosecant go together. Cosine and secant go together. Tangent and cotan go together. So the way I always remember that is every co has a non-co. So in this one, cosecant pairs up with sine because sine doesn't have a co prefix. Cosine pairs up with secant because it doesn't have a co. And then tangent pairs up with cotan. If that helps you, use it. If it doesn't, that's okay. The second thing is we're going to talk about some properties, the reciprocal properties. So sine is reciprocal is 1 over cosecant, cosine is 1 over secant, and tangent is 1 over cotan. So those are all identities that you're going to want to know, and hopefully we'll use them enough that they become comfortable for you. These are all what we call basic identities, so reciprocal properties. Then we have another set of identities down here, which is the Pythagorean identity. And there are 3 of them. Sine squared theta plus cosine squared theta equals 1, plus tan squared theta equals secant squared theta, and 1 plus cotan squared theta equals cosecant squared theta. There are a couple other identities I want to add to this list. So they are quotient identities. And they are tangent of theta equals sine theta over cosine theta. And the second quotient identity is cotan theta, which is cosine of theta over sine of theta. So we're going to work with those basic identities a lot. The other thing I want to kind of touch base with before we start is some notation. that you need to understand. And that is when I see sine squared theta. Notice that little power 2 is not on the theta, it's between the sine and the theta. That's the same thing as saying sine of theta all to the power 2. So if we were doing it for cosine, you would see cosine squared theta, which equals the same thing as cosine theta squared. So this 2 is in front of theta, so it's not just we're squaring the angle, it's the actual identity. So that means sine theta times sine theta, and that means cosine theta times cosine theta. So those are all some of the identities and things that we're going to work with today on these notes. All right, so the first one, problem 1, says find the 6 trig functions of a 5, 12, 13 triangle using triangle trig. Okay, so the first thing I want to do is kind of get a picture and orient myself. So I'm going to make my triangle look something like this. I'm going to put my right angle there. So wherever you put your right angle, just identify that. And I'm going to identify that my theta is in this angle spot right down here. So as we look at the triangle, we need to label the side. So we know 13 is the longest, so that's going to be the longest side in my triangle. And then I'm going to have a 12, and then I'm going to have a 5. Okay? So getting things labeled is important. After we do that, then we're going to go through those 6 trig things that we talked about a moment ago. So if I have sine of theta, remember that is opposite over hypotenuse. So I look at my triangle from theta, the opposite is 12, the hypotenuse is 13. So my ratio is 12 over 13. Okay, then I do cosine of theta, and we know cosine of theta is adjacent over hypotenuse. So I go to my triangle, adjacent is down here. Remember, adjacent means connected. So that's 5, and then the hypotenuse is still 13. So cosine of theta is 5/13. And then we have tan of theta, and tan of theta is opposite over adjacent. And so that means the side opposite directly across from is 12, and adjacent is 5. So those are the 3 ratios you should be able to do from geometry. And then when we add our new ones, then we're going to do cosecant next, because remember cosecant is attached to the sine because the sine doesn't have the co-prefix. And then that's the reciprocal, so now we're doing hypotenuse over opposite, and hypotenuse over opposite then means my ratio is 13 over 12. So cosine is going to be paired with secant, because this has a co and this does not, and it's reciprocal, so it's hypotenuse over adjacent, which means my ratio is 13 over 5. Then the last one is cotan of theta. Those are too easy to remember, go together, cotan and tangent. And so its reciprocal would be adjacent over opposite, which means 5 over 12. And normally I don't put multiple equal signs on the same line, but since we're kind of showing that comparison, that's what I went with. So that's what I mean by finding the 6 trig ratios. All right, next problem. Number 2. And number 2, again, finding all 6 ratios of an isosceles right triangle. So I have to know what that is to be able to draw my triangle. So we learned in geometry that isosceles means it has 2 of the same sides. And if it's a isosceles right triangle, it also has to have a right triangle in it. So when I draw my triangle here, that means this side and this side are going to be the same length, and my pitiful drawing there has a right angle right there. So isosceles triangles mean this one and this one, and it's a 45, 45, 90, right? So that isosceles right triangle means that if you remember your ratios from geometry, the length of this side is 1, the length of this side is 1, and the length of this side is square root of 2. Okay? So how do I know that? Well, I know that the pattern is a square root's of 2. So if a is 1, then this has to be 1 times root 2 or just root 2. So now we go through and we do it all again. So the first one we would do is sine, and we know that this is 90 and isosceles means that these two angles here are the same. So really we should know that that's a 45-degree angle, so that's what theta is. So instead of saying just theta this time, now I can say sine of 45 degrees. Okay, be sure you use your degree symbol. So sine of 45 degrees, sine is opposite over hypotenuse. So in my triangle then, the opposite side is over here, hypotenuse is over here, so that's 1 over square root of 2. However, we know that we don't leave square roots in the bottom of a fraction, so this would be the same thing as if I rationalize it by putting times square root of 2 on the bottom, times square root of 2 on the top. So that actually makes it square root of 2 over square root of 2 times the square root of 2 is the square root of 4, which is 2. All right, then we go on to cosine of 45 degrees. And cosine of 45 degrees, remember, is adjacent over hypotenuse. So I go to my triangle. Adjacent is down here, which is 1. Hypotenuse is square root of 2. So we know that when we rationalize this out again, we're going to get square root of 2 over 2. All right, and then we go to the third one, which was tan of 45 degrees. So when we do tangent of 45 degrees, remember that tangent is opposite over adjacent. And so I know the opposite is 1 and the adjacent is 1. So I have 1 over 1 or just 1. Okay, so remember then we do these in reciprocals. So then I'm going to say sine goes with cosecant. And anytime I have some of this stuff going on, I don't want to use this last one as the reciprocal, because if I do that, I'm putting that radical right back in the bottom. So what I want to use is this one right here, and when I do the reciprocal of that, I just get that that's root 2, because that would be root 2 over 1. And then cosine goes with secant. Oops, sorry about that. A little bit of a delay here. Try that again. So secant of 45 degrees. Now remember, that's reciprocal cosecant. So again, we have this rationalization going on, so I'm going to go back to this one right here. And I know that secant of 45 degrees then is just square root of 2. And finally, cotan of 45 degrees. And then cotan of 45 degrees would be the inverse of tangent, so that is opposite over adjacent. So now it's adjacent over opposite, which in this case makes it very easy to do because it's just 1. So those are the 6 ratios. So again, we know this was a 45, 45, 90 triangle because this is 90 degrees, and if these are isosceles, which means two sides the same, that also means these two angles are the same. So when you divide 90 in half, you get 45 for each of those. And then we know our ratios from geometry say that we have, I use x, some people use a, but it would be x root 2. So that's the pattern that you should be using from geometry. All right, on to question 3. Question 3 says, give an equilateral triangle, means equal sides and equal angles, with sides equal 2 units. Use the triangles to find sine of 30, sine of 60, cosine of 30, and cosine of 60. So given an equilateral triangle, we have a triangle where all the sides are the same. And we know that all the lengths are 2, so this is 2, and this is 2, and this is 2. And in geometry, you learned that you can take and draw that angle bisector there, and it's going to be perpendicular, so you're going to get a right angle right down here. And so if these are all the same sides and we take 180 degrees divided into 3, then we know that all of the angles are 60. So 60 degrees for that side. And if this is 90, then that leaves this side to be 30 degrees. So depending on the angle you're talking at, if you're talking about doing something with 30 degrees, this is the opposite side. If you're talking about doing something with 60 degrees now, this is the opposite side. So we know that if this whole length down here was 2, that now in my new triangle, I know this is 1 and this is 1 because the whole length was 2. So if I have a 30, 60, 90 triangle, then I also should have learned in geometry that this is x, this is x root 3, and this is 2x. And the length of those sides get progressively bigger. So if I'm looking at this being 2 and this being 1, then I know that the length of this side has to be, if this is the smallest side, x, then this has to be x root 3 or just square root of 3. Because if x is 1, 1 times square root of 3 would be 1 square root of 3. So now we have all of our angles figured out, and we can go from there. So let's do the first one, which is sine, here we are, sine of 30 degrees. All right, so sine is opposite over hypotenuse. So I go in my triangle, identify my 30. So the opposite is over here 1, hypotenuse is 2. This is the sine of 30 degrees is 1/2. And then it says sine of 60. So sine of 60 degrees, now I'm down here with 60. Sine is still opposite over hypotenuse. However, we're looking at it from a different angle. So if this is 60, opposite is now root 3. Hypotenuse is 2. So the sine of 60 degrees is root 3 over 2. Then it asks for cosine of 30. All right, so remember that cosine is adjacent over hypotenuse. And so 30 degrees is up here, so the adjacent one is right here. The hypotenuse is here. So then I have square root of 3 over 2. So it all depends on that angle. So now I'm going to do sine of, I'm sorry, I'm not going to do sine. I'm going to do cosine because I've already done sine. So I'm going to do, pencil there, cosine of 60 degrees. So again, I'm back down here to the 60 degrees, and that's adjacent over hypotenuse still. So the adjacent is this piece connected down here, which is 1. Hypotenuse is 2. So cosine of 60 degrees is 1 over 2. So do you see some similarities there? I hope so, because I know that sine of 30 degrees is 1/2, but cosine of 60 degrees is 1/2. So I know 30 and 60 are complementary angles, and so their position in this triangle using the same side develops a little bit of a relationship going on there. Okay, and we'll talk more about that later. All right, so we're going to find the 6 trig functions for this problem. Okay, so you could use whatever symbol. I mean, I think right here that should probably, let's make that all theta. Okay, so it's 2 separate triangles. I'm going to go ahead and work through them just like we've been doing them. What I don't know, however, is I only have 2 sides. So I would need to know what the length of that is and what the length of that is before I could find all of my 6 trig ratios. We know this is a right triangle, so we know that we can use Pythagorean theorem. So I can say 15 squared plus 8 squared equals c squared. So that is going to be 15 squared plus 8 squared is 289. And so now when I take the square root of both sides, I know c is 17. So there is that one. Then I would have to do the same thing here for the second triangle. We've done a few of these, so unless I'm thinking I'm just going to probably do one of these two so we can move on and get through the rest of the notes. All right, so I'm going to do sine of theta because we don't know what the angle is, which is opposite over hypotenuse, or 8 over 17. And then we're going to do cosine of theta, which is adjacent over hypotenuse, which is 15 over 17. And then we're going to do tan of theta, which is opposite over adjacent, so that's going to be 8 over 15. Okay, because remember, everything orients from this angle right here, so this is opposite, this is adjacent. All right, and we know if we do these in pairs, then we can use that reciprocal, so cosecant of theta is going to be 17 over 8, and secant of theta is going to be 17 over 15, and cotan of theta is going to be 15 over 8. So you can go straight through that real quick. If we go ahead and do this second triangle, we need to find the missing side. So I get 7.5 squared plus 4 squared equals c squared. So I get, because I calculated this ahead of time, 72.85, which equals c squared, and c is going to be 8.5. So that's the length of this side right here. Remember, you're doing everything referencing it from that angle right there. So if we go through it again, we get sine of theta equals 4 over 8.5. If we do cosine of theta, we get 7.5 over 8.5. If we do tan of theta, we get 4 over 7.5. I almost used the wrong side. And then it's reciprocal. So cosecant of theta equals, and we would do 8.5 over 4. Secant of theta equals 8.5 over 7.5. And finally, cotan of theta equals 7.5 over 4. All right, let's backtrack here just a little bit because I said one thing and wrote something entirely different. So let me fix that for us. We have cotan of theta, and cotan is going to be adjacent over opposite. So when we set up a triangle, we need to identify the right angle, which I'm going to put right here, and then I'm going to use my theta to be at this angle right there. So then I can lay in what I know, because remember, the cotan is adjacent over opposite, so that means adjacent is 3, so that's going to put my 3 right down here. And then the opposite is 2, so that's going to put the 2 over here. So what I'm missing is the hypotenuse. So again, Pythagorean theorem, 3 squared plus 2 squared equals c squared. And so then I have 9 plus 4, or 13, equals c squared. So c, when I take the square root, is square root of 13. And we're talking distance, so we don't have to worry about that negative possibility. So I now have the length of my hypotenuse, which is square root of 13. So then we are going to find the other trig ratios. We know what cotan is, so we don't have to do cotan. So let's start with sine. So sine of theta, remember sine is opposite over hypotenuse, so the side opposite over the hypotenuse is 2 over root 13. We know we don't leave root 13 on the bottom, so we rationalize. Square root of 13 times on the bottom and the top. And so that leaves me with 2 root 13 over 13. Okay? Then I'm going to do cosine of theta. remember that cosine is adjacent over hypotenuse. So adjacent is down here, hypotenuse is over here. So I get 3 over root 13. Again, we know we can't leave that root 13 in the bottom, so we multiply the bottom by root 13 and we multiply the top by root 13. So that gives us 3 root 13 over square root of 13 times square root of 13, and then taking the square root, which just gives me 13. Okay, so then I can do tangent, which is opposite over adjacent, so the opposite over adjacent, so that one is just 2/3, so we didn't have to actually do any rationalizing on that one, so that's good. So sine, then we would do cosecant of theta, and cosecant, remember, is that reciprocal, and so I want to go back to the one where the rational was in the bottom to begin with. So when I invert it and get its reciprocal, I don't have to rationalize again. And then cosine would be with secant. Cosecant of theta, again, going back to where the radical's in the bottom, is just going to be square root of 13 over 3. And cotan we already had over here, so we don't need to calculate that. So that's finding the other trig ratios. All right, number 6. Given secant of theta equals 5 and tan of theta equals 2 root 16, evaluate the following. So you're going to have to use both pieces of those information to actually get your triangle. So I'm going to draw my triangle. And again, I'm always going to identify my right angle and where my theta is going to be, and I'm going to put it down there. I know you don't always have to put it down there. It's just kind of a habit, but that's okay. So then from secant, what do I know about secant? I know secant of theta is hypotenuse over adjacent. So that is 5 over 1. So in this triangle, the hypotenuse has to be 5 and the adjacent has to be 1. But also in this triangle, tan of theta equals 2 root 6. And so technically that's 2 root 6 over 1. And so we know tangent is opposite over adjacent. The adjacent is 1, which is right down here, leaves the opposite to be 2 root 6. So now I have all of the pieces of my triangle, and I can find the problems that it's asking me to. So the first one, A, is cosine of theta. So in the triangle, remember that cosine is adjacent over hypotenuse. So in this triangle, adjacent is 1, hypotenuse is 5, so cosine of theta equals 1 over 5. All right, and then we have B, and B is cotan of theta. And so remember that cotan is adjacent over opposite. So that means in my triangle, adjacent is right here, opposite is right here, so that's 1 over 2 root 6. And remember, we can't have the root 6 in the bottom, so I need to get rid of the root 6. The 2 is fine, the root 6 is not. So I'm going to multiply the top and the bottom by root 6, which gives me root 6 on top and 2 times 6, which is 12 on bottom, because root 6 times root 6 would be root 36. Root 36 is 6. Okay, so then we are on to C. So C is cotan is 90 degrees minus theta. And what that means is the complementary angle. And so we have a few identities that we can look at that go right there. So I'm going to put these up at the top so that you have them. We will go into much more detail about these identities later on, but these are complementary angle identities. That's theta. So sine of 90 degrees minus theta, so it's saying whatever your angle is, like 60 degrees, 90 minus 60 degrees means I'm finding the sine of 30 degrees, which is the same thing as cosine of theta. Okay, we have tan of 90 degrees minus theta, and that's going to be the same thing as cotan of theta. And then finally we have secant of 90 degrees minus theta, which is the same thing as cosecant of theta. So if I'm finding the complement for this one, the complementary angle for sine of this is cosine of the angle. Okay, so that's how that works. So in this one then, cotan of 90 degrees would be the same thing as finding the tangent of the angle. So what I'm finding is the tan of the angle. Okay, so when I find the tan of the angle, that's opposite over hypotenuse. So the tangent of the angle then is just going to be, remember we're back over here, opposite is 2 root 6, adjacent is 1. So that's just 2 root 6. Okay, and finally D, we're finding sine of theta. Oops. Sine of theta is opposite over hypotenuse. So in my triangle, opposite is 2 root 6, hypotenuse is 5, so that's 2 root 6 over 5. Okay, so that's just another set of basic angles that we're going to work with, and complementary angles is what it is called for. All right, so the last one, guys, cotan of, and that is another little Greek symbol. So theta is a Greek symbol, that's alpha. Looks like a little curly sideways. And it's giving me the fact that cotan of alpha sine alpha equals cosine of alpha. And it's telling me 0 to 2, pi over 2. So what that means in terms of angles at this point, it's 0 to 90 degrees. We're going to talk a whole lot more about what that means shortly, so don't panic. If you don't know that off the top of your head, that's okay if you don't remember that from geometry. We will be coming up and learning how to go back and forth between units of measure, which are radians and degrees. All right, so when we do this, we transform from this side to this side. We're going to go from the left to the right, and when we work on that. So what does that mean? That means you take the left side, which is cotan of alpha sine of alpha, and that's what you're trying to simplify. Okay, so how I simplify is I use some of the properties that we've been talking about. Now remember in the very first I told you there were some quotient identities? Well, this is where they come into play. So what I can do is replace a trig identity with another identity. I'm not manipulating, I'm just replacing. So if you remember from the very first page, cotan of theta is the same thing as cosine of, I'm using alpha, not theta, over sine of alpha. And that is the quotient identity. So let's see, I decided to save right there in the middle of my problem. So let me backtrack for just a minute here and get my alpha there. And then when you see these two side by side, that's the same thing as multiplication. So I'm going to multiply this by sine of alpha. And since I'm talking fractions, I'm just going to put it over 1 because we can make anything a fraction by putting it over 1. So now I'm not going to work on this side at all. Everything is going to happen here. So I'm going to put another equal sign underneath it because we are only going to have one equal sign per line, and your steps are going to go down. This is a variation of learning how to prove. If you go equals, 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 I'm not going to give you credit because that's not the right form. Just like in geometry, you did a 2-column proof. In trig, your proofs run vertical. All right, so what I'm going to do now is I'm going to simplify. And this is, we're actually just simplifying. We're not actually proving or transforming. So I know that anything divided by itself is 1. And so I know in my head this is what's going on. What I also know then is if this transforms to 1 and this transforms to 1, I'm left with cosine alpha on this side times 1 on this side. And that just means I have cosine of alpha left. So it's really using identities. So what I did is I used an identity here. My pen, I think, might be running out of charge here. Let's try one more time. So I used an identity here. Okay, and then I simplified here to get down to what I was trying to prove. So you can see I worked the left side and I ended up with the right side over here. And so that's kind of how simplifying would work on a problem like this. So that's everything from right triangle trig and some basic work and basic properties. Keep your properties handy, and then you will be able to kind of work them enough, hopefully, that you're not really memorizing them at this point. You're just going to use these basic identities enough that you will be able to just recognize them as you go. All right, so go ahead and complete your homework assignment. Keep your notes handy, and we will carry on with applications of right triangle trig next class. Bye, guys.